Let's take a look at a binomial probability distribution. So a binomial probability distribution is a probability distribution where there are two outcomes, success or failure. Alright, I'm going to go over how to tell if a distribution is a binomial distribution, and that should give some insight into what a binomial distribution actually is. First of all, an experiment is performed a fixed number of times, and each repetition of the experiment is a trial. The number of trials is equal to our n. So when we start seeing some formulas that involve this, our n is the number of trials. The experiment can be something like asking a specific number of people a question, rolling a dice a certain amount of times, something like that. The second thing for something to be a binomial distribution is each of the trials must be independent. So you can't have a trial where you're picking a bunch of cards without replacing them. Or any other instance where one event depends on the other event occurring. The third thing for something to be a binomial probability distribution is that for each trial that you do, there are two possible outcomes, success or failure. And success or failure can mean a couple of different things. If you're asking somebody a question, it needs to be like a yes or no. Yes could be success, and saying no to the question could be failure. If you're rolling a dice and you're trying to roll a 6, rolling a 6 could be success, and rolling anything other than a 6 could be a failure. So there's lots of different ways to look at that. And the last thing that has to be true for a binomial probability distribution is the probability for success is the same for each trial. So, for example, when you are rolling the dice, you can get a 6, and the probability of rolling a 6 is 1/6 every time. It doesn't change. So that probability has to be the same for every trial. So just really quick here, let's talk about some of the notation we're going to see in a binomial distribution. N is always going to be the number of trials. So the number of trials is n. X is going to be the random variable, and that is the number of successes. Lowercase p is the probability of success. So that means that 1 minus p would be the probability of failure. Now let's look at some examples where we need to determine if the situations given are a binomial distribution or not. Alright, the first example says 100 children are randomly selected and asked if they have ever been on an airplane. The number of yes responses is recorded. So, if we take a look at this, 100 children, so we have a fixed number of trials. So the first condition for it to be a binomial distribution is satisfied. Each trial is independent. So each kid is independent from each other. Their response does not depend on what another child said. So each trial is independent. So the second thing of the binomial distribution is satisfied. The third thing, for each trial there are two outcomes, success or failure. So the responses the children can give are yes, they've been on an airplane, or no, they have not. So we have two different responses. In this case, our response, yes, is a success, because that is what we are recording. The probability for success is the same in the trial. On that, so we're good. We have a binomial distribution. The second question, treating 112 subjects who get heartburn with a particular medicine. After you give them the medicine, you ask how they feel after taking it. So, we have a fixed number of trials. Each trial is independent. How one person feels isn't going to change how the next person feels. The third question, though, there are two outcomes, success or failure. Does this question have just two outcomes? No, you can have I feel okay, I feel all right, I feel really, really bad, I feel average, I feel great. All of those are different possibilities. Or if you want to set that to a number scale, how do you feel from 0 to 10? That would also not be okay because you have all those different options. So this is no. Because, let's see, because there are multiple, or sorry, not multiple, let's say more than two outcomes. All right, now let's look at the third question. We're going to change that question up a little bit and say we treat the 112 subjects, so we know we have a fixed number, and we record if they have heartburn after 24 hours. So in this case, they're either going to have heartburn or they are not. So because of that, how we change that problem, we've changed question 2 into a binomial distribution. So this would be yes. Number 4 says, 10 cards are picked at random from a 52-card deck without replacement. The number of hearts is recorded. So we have a fixed number of trials. We have 10 trials. We're picking 10 cards. However, is each trial independent? No. So this is not a binomial distribution because the trials are not independent. We're going to look up how to set up a binomial distribution, but before we do that, we need to know what the formula is to find the probability of x successes given n trials, where we have a probability of success for each trial. So we're going to take a look at that formula first. All right, so the formula says the probability of x successes occurring is equal to n choose x, which is really NCR, times the probability of a success to the number of successes power times 1 minus the probability of success to the number of trials minus successes power. So let's look at an example on how to just find the probability of x successes when we have 5 total trials where the probability of success is equal to 0.4. Now that's the probability of one success in each trial, not the probability of success total amongst all the trials. So we have here the formula. We're going to find the probability of 3 successes is equal to 5 total trials where we're picking 3 successes times 0.4 to 3 successes power times 1 minus 0.04 to the 5 minus 3 power. And if we go calculate that out, that probability then will be equal to 0.2304. Alright, so here are the steps on how to set up a binomial distribution. So the first thing you want to do is if you have a probability distribution where there's n trials and a probability of each success for each trial is equal to p, then we're going to make a chart with your random variable x, where x is 0 to n. So the chart will look something like this, where we have our x for our number of random variables and the probability of that many successes in our trials. Okay, then after we find the number of successes, we are going to find the probability of each of those successes by just plugging into this formula. So let's try an example. Okay, create a probability distribution for rolling a die 3 times and recording the number of 4s that happen. So on this problem, our n is equal to 3. That means we're rolling the dice 3 times. That's how many total trials that are occurring. And then the probability here is we're recording the number of 4s. So in one roll, what's the probability of getting a 4? It is 1/6. So 1/6 is my probability for one success. So now we need to find the probability of having 0 successes. So on the 3 tries, getting 0 4s. 1 success, so on the 3 rolls, getting 1 4. 2 successes, and 3 successes. And we're going to find each of these by plugging, respectively, their variable into the formula and the probability into the formula. Alright, so I'll go and plug 0 in for x, 3 in for n, and I'm going to plug 1/6 in for p. And I'm just going to plug it right into my calculator. There's no point in even trying this by hand. So then you plug it in and I've got 0. If you want to pause the video and try and plug it into your calculator yourself, that would be very good practice. So 0.5787 is the probability of getting 0 successes on 3 rolls and having no 4. Alright, if I do the same thing for 1 4 on the 3 rolls, it will be 0.3472. If I find it for 2 successes, then the probability really drops. We get 0.0694. And for 3 successes here, we've got 0.0046. Now, if we add all of those together, they should round very, very, very close to 1. Now, this is all you need to do to set up your probability distribution. All right, the last thing I want to take a look at is the mean and the standard deviation of a binomial distribution. Before I go into the mean and standard deviation formulas, the first thing I want you to know is what the mean actually represents in a binomial distribution. So the mean in a binomial distribution represents the expected value. The expected value is what number you're expected to get every time an experiment is repeated. So some examples of that is when you play the lottery. How much are you expected to win every time you play the lottery? Or when you're rolling a dice and you're trying to find the number of 4s with 3 experiments, how many 4s you're expected to get every time you repeat the experiment. So let's look at the formulas for the mean and the standard deviation. All right, here's our 2 formulas for mean and standard deviation of the binomial distribution. The first formula for the mean, or our expected value, is equal to n, the number of trials, times p, the probability of success. Very simple formula. It's just n times p. The standard deviation for that is pretty simple, and it's built right off of the mean. It's n times your p times 1 minus p, and then you take the square root. The standard deviation just represents how the values are distributed, how the probability is distributed amongst the mean. Alright, so here's an example. According to a survey, 61% of drivers ran a red light last year. For 500 selected people, find the expected value and the standard deviation. Before I use these 2 values, or formulas, let's see if we can figure out what our n and our p are. So the n's fairly obvious. It tells us right there that we have 500 selected people. So that is going to be our n, our number of trials. Our p is the probability of success, so the probability of picking someone and they have ran a red light. So the probability of success would then be 0.61. So let's use the first formula to find our expected value. So we have our mean is equal to n, which is 500, times our p, which is 0.61. And that ends up being 305. So if we were to go ask 500 people, we should approximately get 305 people that say they have ran a red light. All right, so last thing, to find the standard deviation here, we just go the square root of our n times our p times our 1 minus p. And after plugging that into the calculator, we would get 10.91.